Imagine you're in a spaceship accelerating through the cosmos, and suddenly you discover that the very act of accelerating is creating thermal radiation around you, literally heating what should be the icy void of space. It sounds like science fiction, but this is one of the most bizarre and fascinating predictions of modern physics. Today, we're going to dive into the mystery of the Rindler Horizon and discover how simple acceleration can transform the void into a warm bath of ghostly particles. Cosmic explorers, welcome back to Cosmic Frontiers. I'm your guide on this journey through the deepest mysteries of the universe, and today we're going to explore a phenomenon that will completely change your perception of motion, space, and time. We'll discover why Einstein was only scratching the surface when he said everything is relative, and how a physicist named Wolfgang Rindler revealed that accelerating isn't just a matter of speed, it's a matter of reality. We're building an incredible community of cosmic explorers heading towards 1,000 subscribers, and each one of you is helping us unravel the deepest secrets of the cosmos. Before we begin our journey, I need you to imagine something with me. You're floating in space, in a ship that starts to accelerate constantly. Not just any acceleration, but an acceleration that never stops, that continues forever. What do you think would happen? Most of us would only think about the speed increasing, but physics holds a much stranger surprise for us. This constant acceleration would create something around you called a Rindler Horizon, an invisible barrier in space-time that would divide the universe into two completely different parts. Wolfgang Rindler, the Austrian physicist who studied this phenomenon in the 1950s, discovered something extraordinary. When you accelerate constantly through space, your perception of reality changes fundamentally. It's as if the universe divides into two regions, one you can see and interact with, and another that simply vanishes from your existence. But here's the most impressive part. This division isn't just an illusion of perspective. It has real and measurable physical consequences. To understand the Rindler Horizon, let's use a familiar analogy. Imagine you're driving on a straight road and start to accelerate constantly. As you accelerate, objects behind you get further and further away and harder to see. Now imagine that this acceleration never stops, and at some point, there's a line behind you beyond which no light can reach you anymore. This imaginary line is similar to the Rindler Horizon, a boundary beyond which events simply cannot affect the accelerating observer. But here arises the first major difference between our analogy and physical reality. In the case of the Rindler Horizon, we're not just talking about light that can't reach us due to practical limitations. We're talking about a fundamental separation in the very fabric of space-time. For the accelerating observer, everything beyond this horizon simply ceases to exist in terms of cause and effect. It's as if the universe were literally cut in half. Einstein taught us that gravity and acceleration are equivalent, the famous equivalence principle. If you're in a closed box and feel a force pushing you down, there's no way to distinguish whether that force comes from the gravity of a planet or the acceleration of the box through space. This equivalence means that Rindler horizons have a deep connection to the event horizons of black holes. Both represent boundaries beyond which information cannot escape to reach the observer. Now we come to the most fascinating part of our story. In 1976, a Canadian physicist named William Unruh made a discovery that shook the foundations of physics. He demonstrated that an observer accelerating through what appears to be a perfect vacuum, completely empty space, would actually detect thermal radiation. This radiation, known as Unruh radiation, means that the very act of accelerating can make you feel heat coming from nowhere. To understand how this is possible, we need to delve into the quantum nature of the vacuum. What we call empty space actually seethes with quantum activity. Virtual particles are constantly appearing and disappearing in pairs, in fluctuations so rapid that we usually can't detect them. It's like the surface of a lake that looks smooth from a distance, but when we look closely, it's full of small ripples and disturbances. An observer at rest or in uniform motion sees these quantum fluctuations as a state of minimum energy, the vacuum. But an accelerating observer sees something completely different. Acceleration causes these quantum fluctuations to reorganize in such a way that they appear as real particles, carrying thermal energy. It's as if acceleration were a special filter that transforms invisible quantum noise into detectable radiation. The temperature of this Unruh radiation is proportionally small for normal accelerations. To feel just 1 degree above absolute zero, you would need to accelerate at about 25 trillion meters per second squared. an acceleration so absurd that it would destroy any material object. But the principle is real and has profound implications for our understanding of reality. Let's pause to absorb this. What Unruh discovered is that temperature is not an absolute property of the universe. It depends on your state of motion. Two observers looking at the same piece of space can measure completely different temperatures, and both will be correct. An observer in freefall feels no radiation, while an accelerating observer feels heat. Temperature becomes a matter of perspective, just like simultaneity in special relativity. This discovery connects three seemingly separate areas of physics: relativity, quantum mechanics, and thermodynamics. It shows that concepts like temperature and entropy are not just properties of matter, but fundamental characteristics of the geometry of spacetime itself. It's a conceptual unification as elegant as it is unsettling. Now, let's explore the deeper implications of the Rindler Horizon. For the accelerating observer, there is a region of spacetime that is completely disconnected from their experience. Events that happen beyond the Rindler Horizon cannot send signals that reach the accelerating observer. This creates a fundamental asymmetry. While the observer can send signals to the region beyond the horizon, they can never receive replies. This situation is mathematically identical to what happens with black holes. An observer falling towards a black hole can send signals to distant observers, but after crossing the event horizon, those external signals can never reach them again. Unruh radiation has a direct counterpart in the Hawking radiation of black holes, suggesting that these phenomena are different faces of the same cosmic coin. Stephen Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. This radiation arises from the same fundamental mechanism that produces Unruh radiation, the interaction between acceleration, or intense gravity, and the quantum fluctuations of the vacuum. It's as if the universe had a hidden temperature that only reveals itself when you change your perspective of motion. Here's something that will blow your mind. If you could accelerate with enough force, you could literally boil water using only the vacuum of space. The Unruh radiation you would detect would be so intense that it would heat any object around you. Of course, the acceleration needed would pulverize anything made of atoms long before reaching significant temperatures. But the principle remains valid. This connection between motion and temperature has profound philosophical implications. It suggests that properties we consider objective and universal, like the temperature of an object, are actually observer-dependent. There is no true temperature of the vacuum. There is only the temperature that each observer measures according to their state of motion. Rindler horizons also help us understand one of the most disconcerting paradoxes of modern physics, the black hole information paradox. If information falling into a black hole is truly destroyed, it violates fundamental principles of quantum mechanics. But studies of Rindler horizons suggest that information may not actually be lost. It may simply become inaccessible to certain observers, remaining encoded in the radiation that these observers detect. Let's imagine a fascinating thought experiment. Suppose you have a friend floating in space while you constantly accelerate away from them. As you accelerate, you will see your friend moving away slower and slower due to relativistic effects. Eventually, your friend's light will become so redshifted that they will appear to freeze at the Rindler horizon, similar to what happens when we observe something falling into a black hole. But here's the strangest aspect. You will start to detect thermal radiation that seems to come from the direction of your frozen friend. This radiation carries information, a subtle quantum signature of the events that happened beyond the horizon. It's as if the universe were whispering secrets through the heat of the vacuum, telling stories of events you can never witness directly. The physics of accelerating observers also reveals something surprising about the nature of time. For the accelerating observer, time near the Rindler horizon appears to slow down dramatically, approaching zero at the very boundary. Events that happen just beyond the horizon seem to be stretched out over an eternity, creating a deeply distorted perception of time. This leads us to an impressive realization. Acceleration not only changes how we see space, but fundamentally alters our experience of time. An accelerating observer and another in uniform motion literally inhabit different versions of reality, with different notions of simultaneity, temperature, and even the extent of the observable universe. Physicists today believe that Unruh radiation may be detectable in a laboratory using extreme accelerations achieved with high-power lasers or intense electromagnetic fields. Although we don't yet have the technology to create accelerations large enough to directly detect the thermal radiation, related effects have already been observed in analogous systems using ultra-cold atoms and superconductors. These discoveries are revolutionizing our understanding of the fundamental nature of reality. They show that concepts like temperature, horizon, and even the existence of particles are not absolute properties of the universe, but depend crucially on the observer's perspective. It's a radical extension of Einstein's relativity, applied not only to space and time, but to the very laws of thermodynamics. Recapping our cosmic journey today, we discovered that constant acceleration creates invisible horizons that divide the universe into connected and disconnected regions. We learned that this acceleration causes observers to detect thermal radiation in seemingly empty space, and we saw that these discoveries connect relativity, quantum mechanics, and thermodynamics in ways Einstein never imagined. Even more fascinating, we realized that reality itself is more flexible and observer-dependent than we ever suspected. The temperature of the vacuum, the extent of the observable universe, and even which events can influence our experience fundamentally depend on how we move through spacetime. This leads us to a deep reflection on our place in the cosmos. If something as basic as accelerating can change our perception of reality so dramatically, what does that say about the nature of the universe we inhabit? Perhaps we are only scratching the surface of even deeper mysteries, where the boundary between observer and observed completely dissolves. Cosmic explorers, I want to hear from you. If you could accelerate enough to feel the Unruh radiation, what would you do with that power to literally heat the vacuum of space? And here's an even deeper question. Do you think our normal perception of reality might be limited by our perspective of motion through the cosmos? Leave your thoughts in the comments. What mystery of the universe do you want me to talk about in the next video? Wormholes, dark energy, or perhaps the extra dimensions of string theory? Leave your suggestions in the comments. You guide our next cosmic exploration. We're on an incredible journey towards 1,000 cosmic explorers. If this video sparked your curiosity about how physics can transform our understanding of reality, join our crew by clicking subscribe. Like this video if it expanded your cosmic horizons, and share it with someone who also loves discovering how the universe manages to be even stranger and more fascinating than we imagine. Next week, we'll dive into another mystery that will transform your perception of the cosmos. Until then, keep exploring.